So in this video, we'll look at certain properties, which are the applications of the use of the inner product. And once again, we'll look at the motivation of what we're going to do next. So if you recall, in the R2, which is basically the XY plane, we already understand the meaning of dot product of two vectors. Yeah. So, and this is the dot product. So we know how to do the computations. And there's an important point regarding the use of inner product, which is the fact that u dot v, which becomes a number. When you take a dot product of two vectors, it becomes a number, a real value. It's actually the same as the norm of u times the norm of v times cosine theta. Yeah. So if you know this fact well, based on the properties of dot product, it essentially means cosine theta is the same as u dot v at the top divided by the norm of u times the norm of v. And just to let you know, the cosine theta is the angle between the two vectors. Yeah. And just based on this formula, we should be able to find the angle theta now, which is just the same as the cosine inverse cosine of u dot v and top divided by the norm of u times the norm of v. Yeah. So we can use this formula to help us find the angle between the two vectors. And there's a special situations here. So we call u perpendicular to v. So the mathematical notation I'm using right here is meaning perpendicular. So meaning that u and v um, are separated by an angle of 90 degrees, or in radian is pi over 2. So in this case, please recall that when the theta is 90 degrees, we understand that cosine 90 degrees is 0. So if you look at this formula here, and also because of the fact that if you look at the numerator, the norm of the vector is the length of the vector, which must be positive. So it means that this fact automatically gives us the fact that u dot v, which is at the top here, must be 0. Yeah. So I think actually it's an equivalent case. Yeah. When u dot v is 0, it essentially means that the angle must be 90 degrees, which means u is perpendicular to v. So anyway, let's come back to our case. V is a vector space. It doesn't have to be the xy plane. Xy plane R2 is just a special case of a vector space. There are many vector spaces we can talk about, including the vector space of 2 by 2 matrices, or even the vector space of n by n matrices. So now, we'll try to do the same thing as what we have done on the right side of this board. So what do I mean is like this. When you are given two vectors uv in the vector space V, we can define the angle, let's call it theta, angle between uv. And this so-called angle is somewhat abstract because currently our vector space doesn't have to be the R2 or R3. It can be something more abstract than that. So anyway, you can think of it as the angle. So how to compute this angle between the two vectors? Now, we are supposed to have certain inner products defined on the vector space. This is a general inner product. The inner product is really just a special case on R2. So now, we can think of the same formula, exactly the same. The way the angle theta is defined by using cosine theta, which is the same formula as before, but it's just that the definition of inner product does not have to be dot product anymore. Yeah. So now you would see that this formula is really the same as the one you saw on the right hand side. And moreover, we'll look at when the two vectors are perpendicular to each other. And in the mathematical case, the word perpendicular usually is replaced by the word orthogonal. So we call u is orthogonal to v. And To put it simply, you can really think of it in terms of the word perpendicular. Yeah, we always use the word orthogonal instead in the abstract case. If and only if, same thing happens. Instead of dot product, we have to look at the corresponding inner product. It should be zero. Yeah. So now what I've done on this page is really the same as what you have learned in the context of the dot product on R2. Yeah. So let's take a look at certain exercises. So please look at the current problem now. Let's say in R2, you are equipped with certain inner product. We usually call this kind of thing as the weighted inner product. So now it is not the same as the original dot product, but it is an inner product nevertheless. And we will try to compute cosine theta, where theta is the angle between the two vectors given here. Yeah. So now, please, the cosine theta, we know the formula well. The top is the inner product UV. The bottom is the norm of U times the norm of V. And all of this can be computed as usual. So for example, the inner product of UV, we can use this formula now. Yeah. So please plug it in carefully one by one. For the U, which is the first vector, you see, which is just 1, 4. So it's 1, 4. Yeah. And so I should use the blue color instead. Yeah. And then the next one is the V, which is the second spot. You see the second spot is gonna be the given vector V there. Yes, so it's actually 5, 6, you see. So it's 5 and 6. So you can do this calculation yourself. Then you'll get 82, I believe. Yes. So and the top is 82. How about the bottom? We can do similar things and just recall that for the norm of U is the square root of the inner product with itself. And please be careful here, the inner product with itself, we are using the weighted inner product instead. And now, because you are doing the inner product of U with itself, so it means, so I think these two numbers must be the same, if you get my point, because the second vector now is like V. Yeah. Yeah. Yeah, so the first vector, I use the green underline as usual. So please take a look, compare the entries we have. So anyway, if we do this calculation, I think it's square root of 50. And we can also compute the norm of V, which is square root of the inner product of V with itself. So you can do a similar things here. Yeah, so it's 5, 5, 6, 6. Yeah. So anyway, please do the calculation yourself. So I think it's 50 plus 108 square root, please, and it's 158. So it means that for the norm of U is square root of 50, for the norm of V is square root of 158. And of course, you can use calculator to simplify this numerical answer a little bit. And that's the end of this exercise. So let's look at the second exercise here. Now the vector space is the vector space of 2 by 2 matrices, and we are taking the standard inner product, and which is usually defined this way when we talk about the word standard inner product. So first question part A, let's consider the two matrices given here. Are they orthogonal? And please recall orthogonal essentially means the inner product M1, M2 is 0, right? So basically it's a computational exercise where you need to check the inner product of M1 with M2. If the value is 0, then they are orthogonal. If the value is non-zero, then they are not orthogonal. So meaning that we have to do this computation, which means you are doing the trace of the matrix product. The first one is the transpose of M. The second one is just the M2 like this. Yeah. And please do the matrix product yourself. You should be able to get this matrix product, and the trace of this matrix is just the sum of the diagonals. So it's gonna be 67. So now, which is non-zero, right? Because now it means that the inner product of M1 with M2 is 67, which is non-zero. So it just means that M1, M2, they are not orthogonal. Yeah. And that's the way to solve the part A. And then let's look at part B. Part B, let's try to find the angle theta between the two matrices M1 and M2. And please recall that the cosine theta has the formula like this. Yeah. The bottom denominator is the product of the two things. The first one is norm of M1. The second thing is the norm of the M2. And the top was computed in the part A. By A, the answer is 67. So now you still have to compute the norm of M1, M2. And of course, for the norm of M1 and M2, we have to use this formula, right? So which means that you have to compute this. And same thing for the norm of the M2, you have to compute something similar. Yeah. So it's really a matter of doing some computations. So I'm skipping it a little bit, and please check all the computations here. You're able to handle that. So the norm of the M1 is the square root of 30, where the norm of the M2 is the square root of 174. And the next step is to plug it back to the formula. So you should be able to use calculator to compute this answer, which is the answer for the cosine theta. Then of course, the theta can be computed by using arc cosine, right? And that's the end of this exercise. Next. And the next one, please look at the current problems. Two vectors UV are given. You are asked to find the value of k such that the two vectors UV would be orthogonal to each other. Please note that k is one of the entries in the vector v. So vector v is not explicitly given all the numerical values inside it. So please, once again, this question is about orthogonal vectors. So the inner product of UV would be 0. This one means UV are orthogonal. Yeah. These two are orthogonal. I mean, these two are equivalent conditions. And please compute this. Standard Euclidean inner product essentially means the dot product. Yeah. So now, please compute the U dot V now. U dot V equals 0, meaning that I think 5 times K plus 1 times 4 is 0. I'm just doing it as the usual dot product. It means 5K plus 4 is 0. It means K is equal to minus 4 over 5. So all of these are equivalent. So it means that when the K is minus 4 over 5, UV would be orthogonal vectors. Yeah. And that's the end of this exercise, and that's also the end of the video.